Okay. All right, let's just move on. Let me finish up the examples I wanted to do for arc length, and then I'll take questions on the homework. I will just do a few more examples. So let's remind ourselves, what's the arc length formula? L is equal to
Radical 1 plus
okay. Okay, we get it. All right, so that's the main formula, right? So basically, A and B are just the limits of your integrals. It's the interval in which we want to find the length of the curve f of x. We do that by plugging into this formula. The derivation is not that difficult. You can read it in the book. I don't really care what the you don't need to know what the derivation is. But yeah, basically that's it. So let's do some more examples so you can see the kinds of ways that we could phrase this question. We did the first one where we did that whole perfect square thing, and that worked out nice. What about this guy? Find the length of y equals ln of cosine x on the interval 0 to pi over 4. Okay, so what do? Find the derivative, right? This guy is just f of x, right? So we're going to find f prime, plug in this formula. I could have written this as y prime, it doesn't matter. So that's going to be what?
1 over cosine x. Minus sine x.
Minus sine x over cosine x, which is just minus tangent.
This is the homework.
Oh, was it a homework?
Yeah.
Oh, good.
It was secant.
It was
So-
secant, you put it 1 over cosine, but yeah.
It was ln of secant x.
Oh, okay. Well, here we have sine over tangent, so then the length would be given by what formula?
0 to pi over 4.
0 to pi over 4,
1.
the radical of
1 plus tan
1 plus
square
tangent squared.
becomes secant square.
That just becomes secant squared. You take the square root. We are positive on this interval, so the absolute value just gives us the original function, which is secant. Integral of secant. And what's secant of pi over 4? Tangent of pi over 4? Minus ln of secant of 0? Tangent of 0? Is 0, so that's just ln 1, which is 0. So the length of this curve is radical 2 plus 1. So conceptually, there's nothing much going on in the problems here. The only challenge here is the integral that you get sometimes is really ugly. A lot of times you can't do it with the techniques you learn in Calc 2, but of course on a test I give you stuff you can actually compute. Here's another example. Find the length of this curve. Y minus 3 cubed equals x squared on 0 to 8.
Cube root both sides.
What would you do?
Cube root both sides.
Okay, so you have y minus 3 is equal to x to the 2/3.
Plus 2y.
This means that y is equal to 3 plus x to the 2/3. This means y prime is equal to what?
X to the power of
2 over 3.
negative 1 over 3.
Don't tell me you guys forgot how to
No way.
differentiate. Right. So this means the length of this curve is the curve from 0 to 8 of the radical of 1 plus 4 over 9 x to the minus 2/3. Can we do that one? Or do you do that? What would you do here? Ideas?
Trig substitution?
What would your trig sub be?
It would be x to the negative 1/3 equals 2/3 tan theta.
How did you get that 2/3?
Oh no.
Well, you want to write this, you can write this as
Yeah.
a square.
Yeah. So you would
That would
have,
probably be nicer. So you have 2/3 x to the minus 1/3. Now that is squared.
oh yeah, so it would be 2/3 x to the negative 1/3 equals tan theta.
Okay. It's something to try. Let's see. Does it work out? So I said 2/3. This chalk is really bad. 2/3 x to the minus 1/3 equals tan theta. Now what would that do?
Oh, so then you would differentiate.
Differentiate, so the left side becomes
Negative 2/9.
minus 2/9 x to the minus 4/3 equals
D theta. Oh, and then you also have dx.
yeah dx.
Um,
Go on.
What then?
Plug in.
How?
you,
It has to be with something on the top.
you could I don't know.
Take the points, Jhevon. Just take it.
No, come on, work this out. What do you do here? Because this one is doable.
I mean, I have an idea, but it might be more complicated than, yeah.
What do you think?
So isolate dx there, and
In
then
this equation?
yeah.
And then substitute that, and then substitute.
So you're gonna have dx equals this would be minus 9/2 x to the 4/3.
Yeah.
secant square.
Oh,
And then you substitute it in this place, and then make that become a secant. No, I mean like square root 1 plus.
So I have that. Then what?
then you
Replace.
Because this x is a problem.
yeah.
How do we
Oh.
get rid of that x?
I mean, you have 2/3 x to the negative 1/3 equals tan theta, which means.
But it's inside the square root.
No. Back from the beginning.
Oh.
Here?
We defined our.
Yeah.
Okay, so what's your idea to do with that?
Twice the amount. And flip it.
Um,
Square this and flip it. Oh wait, no. What am I saying? Sorry.
How can I use that to my advantage here?
you can flip both sides, so you'd have 3/2 x to the 1/3 equals cotangent, and then x to the 1/3 is 2/3 cotangent, and then you have x to the 4/3, which
Here I
is
have x to the 1/3 equals
3/2 cotangent. And then there you have x to the 4/3, which is just x to the 1/3 to the 4th power.
okay.
So then you you'd substitute 3/2 cotangent theta to the
3/2 cotangent theta.
to the 4th.
Yeah. Secant square.
But yeah, I don't think that helps.
Well, let's see. If we plug that in, what would we get? So ultimately, this means that L would be equal to what? 0 to 8. What would this guy be?
Secant.
That would just be a secant times, this would be minus 9 times 3 is 27 over 4.
But
Well,
what,
it's-
what about the fourth
This,
power?
this is to the fourth power.
Yeah.
So let's just take that constant out.
C.
L equals minus 9 over 2 times 3 over 2 to the fourth. And then what would we have left in here?
Cotangent
1 over cotangent.
Cotangent
to the fourth.
to the fourth
Secant.
theta times secant squared. And what would that work out to? So I have minus 9 over 2, 3 over 2 to the fourth power. What's your idea now?
I mean,
It's integration of secant cube and cotangent 4. So we just split the secant.
well, it's no cotangent. We could try writing everything like in terms of sine and cosine.
And then cancel.
Sine and cosine. Of course, these limits would be x. We'll,
Yeah.
we'll change those later.
Yeah.
So sine and cosine would be what? This is x equals 0, 8.
Have 1 over cosine cubed times cosine to the fourth over
Sine to the fourth.
That's what you said.
No,
So we have cosine over sine to the
cancel.
Now what?
u substitution.
U sub. U equals what?
Sine theta.
Theta.
Sine theta.
So
Minus 9 over 2.
so now we do u equals sine theta. Right, so our du is going to just be cosine theta d theta. So the integral is going to become what? 1 over u to the fourth. So it's this whole thing, 9 over 2, 3 over 2 to the fourth, 1 over u to the fourth du. And that's just ln of u to the fourth, right? Yeah, so this is how it happens. People get through this, and by the time they get here, their brains are so tired. They're like, they see 1 over there, and it's ln, it has to just be easy for once.
Take it.
Don't take it. Don't fall for it. Like it's a trap. It's a trap. Okay, you treat this as u to the minus fourth, and you do the power rule. Right. So that's going to become what? U to the minus fourth. You add 1 to the power, you get u to the minus 3
Negative.
over the negative 3. Right. But we know what the u was. Let's just actually write it in. U was sine. So this is just 1 over sine cube theta between, what would our limits be? When x is 0, what is y? What? Where's our substitution? Here.
Multiple.
Theta 0.
1,
No.
That's a minus 1/3. 0 was actually not
1 over
a nice
0.
point.
Because of the time.
Yeah, because 0
does
zero
not
actually
exist.
doesn't work here. Let's just make it a 1. It's going to be ugly, but whatever. Okay, so if I plug in a 1 here, theta would just be the tan inverse of 2/3, right? Whatever constant that is. So that would be tan inverse of 2/3. You can use SOHCAHTOA to figure out what that is. And if we are at 8, what's 8 to the minus 1/3?
2.
1/2, right? Which is going to cancel that 2, so I just get a third. And so this is tan inverse of 1/3. So I just plug those guys in. So it's going to be, this minus is going to cancel that. 3 goes into 9 3 times. So I'm going to have 3 to the 5th over 2 to the 5th times 1 over sine tan inverse 1/3 cubed minus 1 over sine tan inverse to the 2/3 cubed. and that would be your length. This we could actually compute, by the way, if we cared to, but I don't care. Remember how to do that sine of tan inverse. You set this equals theta, you draw your triangle, and you can figure out what these sides are. You use Pythagoras' theorem with SOHCAHTOA, and you can figure it out. So yeah, so conceptually, these problems are not that bad, which means if it shows up on a final or something like that, the integral itself is where we're going to challenge you. So here's an example of a challenging integral, but which seemed pretty impossible. Like it's something that you're like, can I even do that? My first instinct probably would have been to simplify this. Because this is a fraction here, I'd have combined the fractions and maybe split the radicals up. I'm hoping that something would have worked out. But this approach is also fine. Yeah, that was the last example in this section. So, questions on the homework. So we're going to have questions on the shell method homework and arc length, if you like.
It's
37.
x squared plus, in parentheses, y minus 1 squared equals 1 about the y-axis.
About the y-axis.
Yeah, and it says use whatever method.
Use whatever method. Okay, so this is just a circle. What's the center?
Y equal.
The center of the circle?
Yeah, 0, 1. 0, 1.
0, comma 1,
0.
right?
Yeah.
With radius 1. So the circle is like this.
Yep.
And we want to rotate that around the y-axis.
It's a sphere. It's a sphere.
Yeah, you're just going to get a sphere, which, by the way, I just rotate half of it, because it's just going to revolve on itself. So I just worry about rotating that side. So what method would you choose?
Arc length.
This seems pretty easy, right? I just have one radius here that I'm going to rotate around that. If I'm rotating about the y-axis with this, right? One reason, why would I choose that? What would be the problem with shell here? Or why would it be less desirable?
So it will be
Because your shell would mean you have to figure out the height of this shell, right? And what's the equation of that? Right, you have to like split this circle into two parts, right? One part is going to be what? You're going to have to solve for y here. You're going to get a plus and minus radical. It's going to look like nasty. So I probably wouldn't want to do that. Right, so I'm going to bring this over. I'm going to get 1 minus x squared. I'm going to get plus or minus the square root of 1 minus x squared. So this would be like y equals 1 plus or minus the square root of 1 minus x squared. And then this would be y equals, that would be the plus, this would be 1 minus the radical of 1 minus x squared. Right? And that's just, using that as a height function just doesn't seem like too much fun to me. Although, so now, what would I do here? How does this set up? So if I'm using the disk, what variable should I be in? The y-axis is the line x equals 0, which means this is a dy problem, which means I should look at things as functions of y, which means my r is just going to be right minus left. So it's this function as an equation of y, which is going to be 1 minus y minus 1 squared, right? And then I take the radical. Yeah? But then remember, when I plug into this method, I'm just going to square it. So I'm going to get rid of that radical again. It's actually going to be a nice integral. Whereas if I had done the shell method, I wouldn't be able to get rid of that radical. So it would be sort of annoying to deal with it. Not totally annoying, but annoying enough, right? So this means that my volume of revolution would be pi times the integral of r squared dy. So this is pi times the integral. I'm going to square that, so it's 1 minus y minus 1 squared dy And it's going from 0, 2 to 2. So that would be my equation. 1 minus y squared plus 2y minus 1. And so then that dies. Integral minus y squared is minus y cubed over 3 plus y squared between 0 and 2. So this is minus 8 over 3 plus 4, which is 12. I can think of that as 12 over 3, right? And then that's 4 over 3. If you're doing the shell, it would have looked something like v is 2 pi times the integral. We're going around x equals 0, so it would have to be dx, so I have to solve for that y. It's going to be something like x is 0 to 1, and then this r would be what? X times top curve minus bottom curve. So it's going to be something like 2 times the radical of 1 minus x squared. Not a crazy integral, but it is far more sophisticated than that one, right? Yep. Substitution of 1 minus x squared here would also do this. So either way, it wasn't too bad, but this seemed to me to be the better option here because my height function looks complicated. Whereas in the disk, my radius squared wasn't that complicated. So here my decision is mostly based on what the original function looks like. Other questions? Shell method? Yeah.
Well, considering in test you don't know how the graph looks like, what do you do?
Yeah.
It's like, what do you mean? Like,
So let's say like
This was a circle because of the formula, we know that. But if you didn't know it was a circle, then what were we supposed to do?
well, it depends on the question. I don't really know. Was there a problem in the homework that you didn't know how to graph?
I took a shortcut and googled the graph.
Like, there shouldn't really be anything that you don't know how to graph. Otherwise, from that, you can take clues if you want. Based on what if you know you're going to be dx or dy, just solve for one of the other variables, see what the function looks like that way.
That's what I did for this and got confused. Then I had to just like look for it. I didn't think it was a circle. Like I know it should be like obvious, but yeah.
Yeah, it's a circle. Yeah. You got to remember your algebra and pre-calc. It's just, yeah.
Okay.
Other questions on shell method? Questions on arc length? .4. In arc length? Yeah. What does that say?
Y equals L minus x squared and then interval from 0.
1 minus x squared is inside the ln?
Yeah. From
Okay.
0 to 1.
So find the y prime, which would be here. Minus 2x over 1 minus x squared. So then you're going to throw that into your formula. So this L is going to be the integral from 0 to 1/2 of the radical of 1 plus this guy squared, which is going to be 4x squared over 1 minus x squared squared. Okay? Looks kind of nasty. Is it too nasty? Can we do something here?
Yeah.
What would you do?
combine those two.
Yeah, sort of write it as one big fraction, see if something simplifies. Which, like I said, incidentally, on that horrible problem, the last example I gave you, that's sort of what I might have tried first. Right? Just write this as one big fraction. I can think of this guy, the 1, as 1 minus x squared squared over 1 minus x squared squared. Right? Just combine the fractions. So I have the radical of 1 minus x squared squared, and on top I would have 1 minus x squared squared plus 4x squared. And so what does the top become? 1 minus x squared squared is what? 1 minus x to the fourth, right?
No, 1 minus 2x squared plus x to the 4th.
Right, so this is 1 minus 2x squared plus x to the fourth minus plus 4x squared over 1 minus x squared squared. All of that is under the radical. X. This is 0 to 1/2. This becomes 1 plus 2x squared plus x to the fourth over 1 minus x squared squared. And what's this?
1 plus x squared plus 1.
1 plus
Right, it's 1 plus x squared squared. Right, because we saw that when I expanded 1 minus x squared squared, I got this guy, which looks just like that guy, but there's a plus sign instead of a minus sign, so it's factored. It's probably just that. And we are on an interval where both of these guys give us positive numbers, which means the radical of the square is just the function itself, because the absolute value would give us the original function. So this just becomes 1 plus x squared over 1 minus x squared. And how do we deal with that integral? Long division, right? So it's something that you might think partial fractions for, but the power on top is the same as the power on the bottom, so we're going to do long division or some sort of algebraic manipulation here if you want. So what's it going to become?
Minus 1.
Minus 1?
Plus
2 over 1 minus 1
1
minus
minus.
x squared.
So that would give us minus 1 plus x squared plus 2, which gives me the 1. Yeah, so you do the long division, that's what you're going to get. And this is 0 to 1/2 minus 1. How do we do this guy? Partial fraction is going to be a 1 minus x and a 1 plus x. What goes over the 1 minus x? Right, so this is 1 minus x times 1 plus x. So 1, if I plug it in here, I would get 2 over 2, which is 1. If I plug in a minus 1, I get 2 over minus 2, which is a minus 1. So this is just minus x plus ln of 1 minus x minus ln of 1 plus x. So this is minus 1/2 plus ln of 1 minus
It should
1/2.
be plus 1. If it was like, no, it's 2 or minus 2.
What?
You have
Plus, wait,
it should be plus
ln.
1 over 1 plus x.
this is the plus here?
Yeah.
That's
Because
plus.
you
Yeah,
have negative
plus
1,
over.
1 minus negative 1 is positive 2, and 2 over 2 is 1.
Plus.
Yeah, that's plus.
This is a plus?
Yes.
And this is a minus?
Yeah,
No.
no, that's
No,
that's
they're
by
all
default.
plus.
So, oh, because this is minus.
Yeah.
Okay, all right, yeah. So that's a plus. So we plug in a half, you have 1 minus a half is a half, plus ln, plug in a half here, you get 3 halves, minus 0, plug in 0 here, you get ln 1, which is 0, plug in 0 here, you get ln 1, which is 0. So that's just the answer. You could simplify a bit if you wanted, but that's fine.
The integral of 1 over 1 minus x is negative L.
So there was a minus. I was wondering where that
No, I
was.
mean,
Here,
Yeah,
Yes.
yes.
So that's, yeah.
that's a minus, that's a minus.
Because of the integration.
Okay, good. Other questions?
Meaning of like.
41.
What? No. Why no?
What?
No,
What happened?
it's
7.3.
7.3. 7.3. Okay, we're going back now.
What? I thought we were done with 7.3.
That's
How much time do we have?
we don't.
lot.
No.
Last question. 41? You guys are trying to stall me.
A right circular cone with height h and base radius r.
Oh, those ones.
Right circular cone, height h, base,
Radius r.
radius r.
Base radius r.
The base radius is r. Yeah.
Okay. What are we supposed to do? Just find the volume?
With Sean.
Well, you could use any method you want. How would you figure that out? So I just basically try to rotate a triangle around one of the axes. Right? So I can just draw a triangle here. I want my height to be h, so this is at a level of h, and my radius is r, so this is at r, which means I can figure out what the equation of this is, right? And what is that going to be? Minus h over r x plus what? Plus h minus h over r. Right, so at this point when my x becomes r, I get h minus h, which gives me the y value 0. When my x is 0, my y value is h, so that's actually the equation of the line. Okay, so I can just rotate this guy around the y-axis and figure out what the volume of this cone is. So what method you want to use? Either of them is fine here, really. Huh?
Shell method.
You want to use shell?
No, we have to.
They said we have to?
No.
The question.
Well, either one could work here. It really doesn't matter that much. Okay, so we could have done that here. That's r. The other r, the radius, let me call it big R. So then our big R is equal to what?
X minus 0.
X minus 0, so that's just x. Our h would be equal to just this function here. H minus h over little r times x. And so this means that the volume of this guy is 2 pi times the integral with respect to x. We're doing it so the limits are from 0 to r of r times h, which is x times h minus h over r x dx. It's 2 pi between 0 and r. This is hx minus h over r x squared. Integral of this h over 2 x squared minus h over r, h over 3r x cubed between 0 and r. Plug in 0, everything's going to die, so I just plug in r. So this is h over 2 r squared minus h over 3 r squared. So that just becomes 2 pi r squared h over 6, right? So then that just becomes 1/3 pi r squared h, which you remember from algebra is the volume of a cone. So yeah, now if you forget that, just do a quick shell method on the side. Like, what's the volume of a cone again? Wait, would we actually need that? Well, we are going to be doing a lot of volumes in the next section, so hopefully you remember some of your volume formulas. Yeah, but if you ever forget, what's the volume of a sphere again? Just rotate a circle around the y-axis. You're done. Oh, well, I have two coordinates, r comma 0 and 0 comma h. Do the slope y2 minus y1 over x2 minus x1. The y-intercept is h, and then this. Right, so you do 0 minus h divided by r minus 0, and that gives you the slope part. just do the y equals mx plus b thing and figure it out. So I had a handout for the next section because some of the problems are a lot of writing. There are a lot of word problems in this section. I didn't want to write everything out. Let's just do it. You know, finally, we're going to do some real work in this class. Work. Since I don't have my handout, let's keep things simple. I'm going to give you the physics definition of work. Basically, it's the amount of effort to get something to move. That's basically what we're going to think of work. In general, well, let's do some preliminaries here. Preliminaries. How about force? What's a force? Basically. Yes, Newton's second law says that this is mass times acceleration.
By changing momentum over time.
Okay, you're smart, you get it.
Or
Right.
gravitational force.
Basically, ideas of push or a pull or a twist. That's the intuitive definition of it. Well, let's talk about units of force, like some common units of force. Newtons,
Changing the square.
right, which is abbreviated N. Can you, right? That's not a unit of force. That's a unit of work.
No,
Yes, that's a unit of force, right? Because a Newton is what? A kilogram per meter per second squared, right? Which is mass times acceleration. Kilogram is the unit of mass, right? So that's a unit of force. Any other units of force that are common to the Americans, for example? Something like foot-pounds.
Wait, that's a thing?
Yeah. Right? So that's a thing. So things like foot-pounds or newtons is something that you'll see pretty often. I don't think we're going to go beyond that. Let's talk about units of mass. Let's talk about mass. Common units. What's like a common unit for mass?
Grams, so kilograms. That's not unit, kilograms.
Here I just wanted pounds. Work is foot-pounds. Common units like grams. If you see grams, that's a unit of mass, right? That's called abbreviated G. Kilograms is also a unit of mass. Abbreviated kg. This, by the way, is the standard international unit, right? So physicists would use kilograms instead of grams usually. Hence, that's what they used here to get the unit of force, right? Where you can sort of see what force is here. We're going to think of it as a product, which is what we've been doing here. Right, so if you see pounds, you should realize that that's a unit of force. And work, as we're going to start to think of it, is going to be thought of as force times distance, right? This is going to be a basic idea that we're going to be playing with and expanding. So basically, how hard do I have to push this object for what distance is, roughly speaking, the amount of effort I have to spend in moving the object, right? So that's what we're talking about when we talk about work. So for example, in American units, if I look at force like pounds, and I look at distance in feet, that's where I get the unit foot-pounds, right? So one possible unit here is foot-pounds. Pretty common in the American circles. Newtons is more common in everywhere else, and in physics.
Where it's important.
Yeah. So I just want to make sure that we sort of know what units to look at, because the problems will often have units built into them, and you need to know what they're talking about. You need to know, if they say grams, they're talking about mass, right? Or if they say kilograms, they're talking about mass. If they say pounds, they're talking about force, right? You need to actually know these things. So, Any other units that pop up, I'll talk about, but these are the main ones, right? So in the metric system or the physics system, you'll use newtons, kilograms, meters, and seconds. In the American system, a unit of force would be pounds. Mass is usually grams or kilograms, and work would be force times distance, and depending on the original units you use for the previous ones will determine how the units for work will look. So basic formulas. If the force, let's call it F, is constant, then work is equal to force times D. This is the force applied to the object. This is the distance the object has moved. And W will be the work. Used in moving an object. In the case the force is not constant, say f of x describes the force exerted at location x, then
Integration 0 x.
you're going to use the integral. The work to move an object from position x equals A to x equals B is the integral from A to B of f of x dx. Right? The idea is if your force isn't constant, you sort of break it up into little infinitesimal chunks. Right? So you sort of dissect your force of how it's moving. And in each infinitesimal chunk, you do a force times distance. You sum over all these distances. You take the limit as the amount of chunks you use goes to infinity, so you get this continuous curve. And you basically get a limit of Riemann sums. And you will end up with this sort of concept here. So these are two very important forms. We're going to be using them all the time. Work equals force times distance. If the force is constant, this is what we're going to use. As long as your force is variable, meaning at a certain position, the force might change on you, and you can describe it with a function, this is what we're going to use for work.
Okay, so what else do we have?
Something else I forgot to mention about units. Suppose units. This is all in the handout. I didn't want to have to write all this down. Give you guys a handout later. Say
I can upload it.
we are given grams or kilograms. Right? How would we obtain the force associated with this? Right? So that's my question to you. So here's an object sitting on a table, and let's say I told you it weighs 5 grams. How much force does this object exert on the table just by being there?
Not something.
What would you do?
Convert 5 to kilograms and then times 9.8.
Right. Remember, a lot of times we're going to think of many cases when the only thing that we care about is the object's weight. In many cases. So we need to do a little bit of physics here, but it's not. Well, it's kind of a lot of it. In many cases, we care about an object's weight. To find this, you use basically weight equals mass times gravity. Right? Basically, mass times acceleration. Weight is a force. So that's another thing you have to know. Weight is actually a force. So we would use mass times gravity. Right? Gravity, we actually need to know what that is. Gravity. This is the acceleration with which you are pulled to the earth. What is the constant for gravity in terms of the SI units? 9.8 meters per second squared. Right? So that's how your speed would change if you're just free falling to the earth in terms of meters and seconds. What about in terms of feet per second squared? Turns out it's 32. Right? So those two numbers you're going to need to know, right? So you're going to read a lot of word problems and they're going to be describing things to you. So they might tell you, oh, if they mention all their distances in feet and pounds, you know you're using the American system. And so at any point you need to apply gravity, you'd apply it using the constant 32. A lot of times it will be thought of as negative because it's acting downwards. Gravity will always act downwards. Minus 9.81 would be according if you tell you the distance in terms of meters. Right? So these are two important numbers you need to know. Okay. So units of force, units of work, units of distance, units of mass, you need to know what all those guys are. I'll just quickly tell you the common ones here. So let me mention that some of these things you need to know. Units of force, mass, length, or distance, volume. That's going to be important later, as you can see. You should know when someone's talking about a volume, or a force, or a mass, or a distance. Gravity, acceleration. Later we're going to need to talk about velocity, not necessarily in the next section, but we will do that eventually. So you should sort of know what these units are. So make sure you know that. Both for the standard system of units and the imperial system of units, which is the American set of units. You also need to know these two formulas, force times distance. We're even going to be using this in the case where we're building up an integral, which you will see pretty soon. So those are just some preliminaries. I had them all on a handout, but now I just have to regurgitate them quickly. Let's move on. There's a very important law. That deals with springs. It's called Hooke's law. It's going to be one of our first applications of work.
Okay, so
Right? What does Hooke's law say?
spring constant. Yeah, F equals negative kx if you want to go. Okay, maybe not.
Right. Hooke's law it talks about an equation for a spring. It says x equals k times x. What is F?
Force.
Force to do what?
So you compress or
Compress, force, stretch, a spring
Without breaking it.
by X units without deforming the spring, right? Because then all bets are off. X is the distance it is stretched or compressed. It is stretched, compressed. With what qualification? Beyond what?
Is it good?
Its natural length. Right? K is the constant of proportionality. This is called the spring constant. It'll be different for each spring. Right? It's something you'll figure out from the problem. Right? This is basically Hooke's law. It's a very important equation in physics that deals with a spring mass system. If you do physics or differential equations, you will see it again, so don't worry. We're sort of breezing over the mechanics of doing problems here. You will definitely look at it again at some point and talk a lot more about it. All right, so this is the first application we're going to use here in the work area with the work on a spring, right? So basically, let's do this. Okay, fence. Okay, tell me the work needed to move a spring. Integral A to B. So I'm going from A units beyond its natural length to B units beyond its natural length, right? To what?
Kx dx.
Kx dx, right? Because we had that formula originally, that work is just the integral of f of x dx. For springs, the force is just k times x, right? So for a spring, this is going to be the equation you're going to use.
Half kx squared.
So this is the work to extend the spring from A units beyond its natural length to B units beyond the natural length. So this is for springs using Hooke's law to find F. This is by no means the most exotic form of work we're going to be doing, so let's just jump into some examples. Example. A spring has length 15 inches. A force of 750 pounds. Well, that's a lot of force. Is needed. It's a really strong spring to compress the spring to 12 inches. Find the work done. Or the work needed. To compress it an additional 3 inches. So problem might look like that. Very standard problem, dare I say even easy problem, which you'll see when we get to the last part of work, you'll see like this is going to be one of the easy problems. Okay, so tell me what are you guys thinking? What are you going to do here?
Yeah.
You need to figure out that force equation. So what's the force equation?
Okay.
What do we know so far? So again, remember, one of the things we're going to be doing is we're going to be reading these problems very carefully. And we're going to be looking out for units. So I see something like inches here. What is that talking about?
Distance.
It's a length. It's a distance, right? When I see pounds, that means force. So this guy here, that's already telling me that's my F, right? This is telling me the natural length. This guy is telling me the distance I can compress it by, right? So if I'm starting out with F equals K times X, my F is going to be 750, right? My K is going to be here. What's the X going to be? 3 inches. Right? Let's keep the units in inches just to be simplistic, right? So I need a force of 750 pounds to compress my spring by 3 inches beyond its natural length, right? Notice that I don't put the 15 here and I don't put the 12 here. X is I have it here. It's stretched beyond its natural length, right? You're just measuring the distance between its natural length and the position you're currently at. Right? So that's going to be my thing. So then I can figure out what K is. K is just going to be 750 over 3, right? Is that a nice number?
25. 250.
What?
Never mind.
250.
Yeah.
So
I was saying the answer 250.
okay, yeah. So that's K is 250. Okay. So now what is going to be
Unit.
my setup?
We'll find the force.
So this basically means that my f of x is equal to what?
250x.
250 times x, right?
Just integrate.
Now we know that work is equal to the integral of f of x dx, right? That's one of our basic formulas. This means I'm going to be integrating the function 250x dx. Okay, so question, what are the limits going to be on my integral?
15 to 18.
No, 0 to 3.
Read the question carefully.
Oh, 12 to 9 or 9 to 12, right?
No.
No?
9 to 15.
Think of equilibrium. How far beyond its natural length am I starting?
12, so 3. 3 to 5. Or 3 to 6. Just say.
Look at the question. It says additional,
Just 3 more.
right? So I have this spring. I compress it by this, right? I already expelled some work. I don't care about that. I want to know how much work to push it further by 3 inches. So where's my starting point?
12.
12.
You're compressing it down, so it shouldn't from larger to smaller.
9 to 12.
Sometimes you need to stretch it out.
Okay, so if I was at 15, I moved it, now it's to a length of 12. How far beyond its natural length am
3.
3.
3 to 6.
I? Right? Now if I compress it a further 3 inches, how far beyond its natural length am
3 to 6.
I? Right?
Yeah.
You're not measuring the actual units you see here. It's x is measuring the distance beyond the natural length. So you're always thinking of the difference between the natural length and the current position. Right? That's what you're looking at. That's where you're basing it from. So then this would be integrate that. What do you get? Over 2 x squared between 3 and 6. Well, 250 over 2 as well.
125.
X squared 2 6 and 3. What do we get now? So we get 125 times 36 minus 9 equals 125 times 27. What are the units here?
Wait, it's work, so that means feet thing.
Remember, you think of force times distance.
And feet.
Our force is in what?
Pounds.
Right, our distance was in inches.
Inches.
So it's inch, and the force was in pounds.
I see.
So, like, inch pounds is a unit. You could also use foot pounds. It's a common unit. So that is an example. Yeah, I only did one example because these problems are kind of the easy ones. But in this one example, there is actually a lot to learn. It's really a heavily packed example. One, you need to notice how the limits of your integral are set up for the spring, right? These numbers are describing the distance beyond the natural length, right? So in this case, I was already 3 inches beyond the natural length. That's why I have to put a 3 here. If I was stretching it from its natural length, it would actually be 0, right? So on and so forth. So I went from 3 inches beyond the natural length to an additional 3 inches beyond the natural length, which means ultimately I end up at 6 inches beyond the natural length. So these distances here are beyond the natural length. For the case of a spring, you're always integrating kx. You can figure out kx, they'll usually give you information to figure that out. They'll tell you what force you need to stretch how far. You plug those numbers in, right? Again, we're plugging in the distance beyond its natural length that we're stretching. So here we went from 15 to 12. The difference in that is 3, therefore I use 3. We're always talking about the difference between the natural length of the natural length to the ending position. Right, so those are just some of the ideas that are really important here. Let's do something more interesting. There are a couple of Hooke's Law problems from your homework, so you'll get more practice on that. But there are also many variations to this work thing, so I really want to get to some different examples. And I sort of categorize some of them. Probably the only one I'm going to be able to get through by the time class ends is the lifting case, lifting problems. Right, so that was the spring problems, which usually will involve Hooke's Law. Now we're going to talk about lifting problems, the work in lifting an object, right? The principle we're going to be using here, which I'm going to illustrate, so don't worry if you don't understand what I'm writing right now. Find the work done moving infinitesimal the object. Right, it just means a very small portion, like a delta x part of the object. We're going to be using that. Use work equals force times distance formula. Integrate to find. I should probably write this out like steps, because this is sort of the order that you're going to want to attack these problems in. So 1, find the work done in moving infinitesimal length of the object. 2, use that formula. 3, integrate to find the total work. Often you will want to begin by drawing a diagram. We like pictures. They just sort of give us ideas of how to set things up. So let me do an example. So you can see what a lifting problem might look like. A 100-foot cable weighs 300 pounds. It's a big metal cable and hangs off the side of a building. Find the work needed to lift the cable to the top of the building. This is a lifting problem. I'm talking about lifting an object. So here's a question. Why can't I just do force times distance here? Because I can't. What are some ideas to consider here? Huh? It gets lighter as you pull things up. You're not always exerting the same force, right? When you're pulling up the whole 300 foot of rope, you have to do a lot of work. But after you pulled up like 200 feet, you can use less force now because you only have 100 feet left to pull up, right? So the force is actually changing as you're pulling the thing up. So the force is actually variable here, right? So that's one of the big things you need to consider. So it's not just a simple, oh, force times distance, right? We sort of, you can think of this as we're moving the object in pieces. At any given time, we're moving a little bit of the rope at a time. So that's what I'm going to call an infinitesimal, right? I'm going to slice up the rope into a lot of little pieces and just worry about what it takes to move that one slice of rope up the top of the building, right? Then I'm going to integrate in general to figure out what is the total work needed. That's the idea, okay? So here, I would start by drawing a diagram, right? So let's say here is my building. Here is the rope hanging off the building. Right? Doesn't have to be amazing. Okay, so that's my diagram, right? Another thing that you'd want to do is you'd want to start to set up things in terms of some sort of naive coordinate system. Personally, I like putting the origin at the bottom, but you can actually choose wherever you want to put the origin. So let's say at this point, I'm going to call the origin 0. Right. Later on, conceptually, you'll see that it often works out nicer to put the origin at the bottom. Okay. So my origin at 0 here, which means the top of the building is what? Would be 100, right? Because I'm basing my origin to be where the edge of the rope is, right? So x equals 0 is this position, the position of the last part of the rope. X equals 100 is the goal, right? I need to move all objects to that distance, right? So what we're going to do, we're going to use our knowledge of integrals. Slice this up into very small pieces, right? And worry about moving the little pieces at a time. Because if I'm talking about a little piece, it's pretty much force times distance, right? So what I'm going to do is I'm going to cut a piece of this rope of length delta x, right? And I'm going to figure out what is it going to take me to move that piece to the top, right? This is sort of the idea, right? Let's consider this being at location x on my rope, right? So x is the distance to get to that location. What is the remaining distance to move the object? 100 minus x, right? So if this is at location x, then the remaining distance is 100 minus x, because the whole distance is 100. Take 100 minus x, you get that distance. Okay? So that's sort of a basic setup of this diagram. Now let's worry about the work to move this one slice of rope. Right? This is now just an object. I just take it and I move it that distance. So what do I think of the work? How do I look at that? Just force times the distance I have to move. Right, so let's start there. The distance I already know. The distance is going to be 100 minus x. What is the force going to be?
300?
32. Well, right.
Why would I use 32?
We're at,
Let's look at force.
pounds.
What in my question is telling me about force?
300.
The 300 pounds is my force. Now, how do I apply that here?
It's only a part of it.
The whole thing weighs 300 pounds, right?
Mm-hmm.
What does this weigh? What is the force applied to that piece of the rope?
300 minus still
300 minus 300 over 1 minus
300 pound times the other.
What?
The mass times.
Wait, is it uniform? Can we like take it as uniform?
Yeah, assume it's uniform.
So, 300 divided by infinite.
Well, let's look at it another way. How much would 1 foot of this cable weigh? Hmm?
3 1 over
3, right? So if I look at, let's look at the unit force. Right? So I know it weighs 300 pounds per 100 feet, right? This gives me 3 pounds per foot, right? Means each foot weighs 3 pounds. Right? So 1 foot will exert a force of 3 pounds. How much does delta x feet exert?
3x.
3 times delta x. Right? Just think of how much you used to do 1 feet and whatever length is you multiply that. Right? So for example, how much does 2 feet weigh? It's just 2 times 3, it weighs 6 pounds. How much does 3 feet weigh? Well, 3 times 3 weighs 9 pounds. Right? Whatever the length you want to figure out what it weighs, you multiply by the unit force, it tells you how much force is applied to that distance. So here I have a length of delta x. Each foot weighs 3 pounds, so the force exerted by that is 3 delta x. Right? So now my work I can write as 3 times 100 minus x delta x. Right? So what I think the total work looks like. Basically, this is going to be your
dx.
f of xi times delta x in your Riemann sum. Your delta x is going to become that dx at the end. You're going to be integrating because you're summing up all these forces, right? Basically, you do this process over and over. You have all these little delta x's that you're moving. They all have to travel a distance of 100 minus x. They will all weigh 3 times delta x, whatever length they are, right? So I'm going to be integrating 3 times 100 minus x. What is the distance here?
0 to 100. Well,
Right, I want to move the entire rope, right? So all points from 0 to 100.
Yep.
So in this conceptualization of work, the limits describe the length of the object you want to move. So I want to move the length from 0 to 100, real quick. So what is the work here? Zero to 100,
What?
it's just 3 times 100 minus x. So that's going to be 3 times 100x minus x squared over 2. From 0 to 100. This would give me 100 times 100 minus 100 times 100 over 2,
oh, you factored me out.
which just gives me 100 times 100 over 2. So that's 50 times 100 It's 5,000 times 3.
It's 15,000.
1,000. What's my
Pound.
units?
Pound, inch, pound feet.
Pound feet. They usually write foot pounds.
Pound. So, this is so ridiculous. Foot pound, like seriously.
Yeah, do that.
It doesn't make sense.
Yeah, we do that.
A foot pound.
Let's make the problem harder.
This is easy?
This is easy.
Jhevon, any chance you're teaching 208 next semester?
Okay, so let's see what we're doing here. So we got that. Okay. Part B. There is a 100. Did I say 1? There's a 500-pound weight attached to the end of the cable. Right, so we're using the cable to transport this 500-pound object. Right, so we need a big metal cable to pull up a 500-pound object to the top of a building. Okay, what's the work? Needed to pull the object to the top.
I just feel like
And off a building. So ignore this part now. We're doing part B.
63x plus 500. Pretty much.
Right. So I have a 100-foot cable, weighs 300 pounds, hangs off the side of a building. There's a 500-pound weight attached to the end of this cable. What's the work needing to pull the object to the top? Okay. What are we gonna do here?
We'll do the same thing, but for 3x, we will just have this 500 not change weight. So it'll be outside the neutral. Or no, no.
How would you think of the work here? The idea is you can think of them both separately, right?
Two different.
The work is going to be the work to pull up the rope itself,
We already found that.
plus the work to pull up this weight,
It does not change mass.
right? This we already found. You would have set it up just as how we did before. That's 1,500 foot-pounds, right? So what's the work to move this weight?
Force times distance.
Because it's a constant force. The thing is just weighs 500 pounds, so pretty much force times this.
Is it 1,500 or 15,000?
15,000.
I'm done.
That's basically it. So that's actually what? So that's 15,000 plus 15,000.
30.
What?
Yeah, I got 15 plus 15.
So, yeah, that part is easy. Again, I could make the problem harder. So, on a final or something like that, I might say something like, okay, we're pulling up a rope. Attached to the rope is a bucket with some water in it.
What
The bucket has a hole in it. It always has a hole. So the water is leaking out as I'm pulling up the bucket. By the time the bucket gets to the top, all the water is gone. I'm like, oh my God. How much work did I do for nothing?
Are you serious?
Yeah, I can actually ask you that question.
Do the same. Just, you know, give the points.
Yeah, which was the next example, but we don't have time to go through it. So yeah, next time we'll look at that. Look over work very slowly, look up those units that I mentioned. look up Hooke's law and just this naive case of lifting problems, and we'll do a lot more on them on Thursday. And then we'll also do pumping problems. And I'll try to remember the handouts, so I don't have to write down the problem.
You want to calculate it?
You can just close it.
First time.